Alright, in this video we're going to look at converting rectangular equations to polar equations. In a previous video we looked at converting a single rectangular point to its polar equivalent. In this one we're going to convert an entire set of points from rectangular to polar form, because that's all really equations are, they're just sets of points. So we can use the relationship between rectangular and polar coordinates to convert equations of one form to the other. In this video, we're going to convert from rectangular to polar, and in the next one, we'll go backwards from polar to rectangular. So for this one, we're going to use the relationship that x is r times the cosine of theta, and y is r times the sine of theta. And in the next one, we'll look at the x squared plus y squared is r squared, and that tangent of theta is y over x. So example 4, we're going to convert each of the following to polar equations. So we have y equals negative x. This is a line with a slope of -1 that goes through the origin. So looking at what y and x represent in their polar form, y is r sine theta, x is r cosine theta. So substituting those expressions in, we have r sine theta equals negative r cosine theta. And if we add r cosine theta to both sides, we get r cosine theta plus r sine theta equals 0. We can factor an r out of each of these two expressions, and that gives us r times cosine theta plus sine theta equals 0. Now that's going to set either r equal to 0 or cosine theta plus sine theta equal to 0. We can ignore the r equals 0, and we can focus on cosine theta plus sine theta equals 0, which gives us cosine theta equals negative sine theta. In other words, the angle at which, or angle or angles at which the cosine of the angle is the opposite of the sine of the angle. Now, between 0 and 360, or 0 and 2 pi, we have 3 pi over 4 where that happens. We also have 7 pi over 4 where that happens. Here, I just went with negative pi over 4, but you could have said 3 pi over 4 or 7 pi over 4 or anything to that nature. Again, just like with rectangular coordinates in polar form, there's an infinite number of polar representations. We actually also have an infinite number of equivalent, because of the coterminal angles, equivalent representations here. So this is just an angle that makes a negative 45 degree or negative 5 pi or negative pi over 4 angle with the x-axis. So it would look like a line where the slope is -1 and the y-intercept is 0, is at the origin. Part B, y equals x squared. This is a parabola where the vertex is at the origin. So r sine theta equals r cosine theta being squared. That gives us r squared cosine squared on the right. And if we subtract from both sides, we get r sine theta minus r squared cosine squared theta equals 0. We can factor out an r from both of those, and we get r times the expression sine theta minus r cosine squared theta equals 0. We can then set each one equal to 0. We can ignore the r equals 0, and we have sine theta minus r cosine squared theta equals 0. So working with that, if we add r cosine squared theta to both sides, we could have subtracted the sine theta and then divided by -1. But to avoid all those steps, just bringing over the r cosine squared theta. And then divide both sides by cosine squared theta. And we have sine theta over cosine squared theta is sine over cosine times 1 over cosine. Sine over cosine is tangent. 1 over cosine is secant. So the polar representation of a parabola with the vertex at the origin is r equals tangent of theta times secant of theta. Part C, x minus 3 in parentheses squared plus y squared equals 9. This is a circle where the center of the circle is at 3, 0 on the x-axis, 3, 0, and then the radius is 3. So we're going to see the polar representation of this equation. So let's substitute r cosine theta for x and r sine theta for y. We get r cosine theta minus 3. That whole expression is squared, plus r sine theta, that expression is squared, equals 9. Expanding out r cosine theta minus 3, when we square that, we get r squared cosine squared minus 6r cosine plus 9. And then squaring r sine theta, we get r squared sine squared theta equals 9. Here, if we subtract 9 from both sides, we get r squared cosine squared theta plus r squared sine squared theta minus 6r cosine theta equals 0. So again, subtracting the 9 from both sides, now we have it equal to 0. In our first two expressions, we can factor out an r squared, giving us r squared times cosine squared plus sine squared. And cosine squared plus sine squared, as you'll recall, is always equal to 1. So we get r squared times 1 is r squared minus 6r cosine theta equals 0. So each one of these has an r that we can factor out. So we have r times r minus 6 cosine theta equals 0. So if we set each one equal to 0, we can ignore the r equals 0, 1. And then we have r minus 6 cosine theta equals 0. So adding 6 cosine theta to both sides, we get in polar form the equation of a circle where the center is at 3, 0 and the radius is 3, much simpler in polar form, is r equals 6 cosine theta. And if we kind of think of the nature of the polar coordinate system, it is tailor-made for equations of circles because that's essentially what the polar coordinates are based off of. So a little bit easier polar representation for a circle than in the rectangular one. All right, so that about does it for this video. Thanks for watching. I'll see you next time.